Hello everyone, welcome back to the latest lecture session. Without wasting further time, I will discuss the relevant aspects. First, let's take a holistic view of where we are. Wastewater is coming in. I want to treat that because it doesn't, or I do not want it to contaminate and pollute my surface water bodies like lakes, streams or rivers. So, what is it that I need to do? I need to remove some particles, let's say, or decrease some variables. What am I concerned about? First, grit. So, for grit and other aspects, I have preliminary treatment, right? And this I also need to pump the water up if required. So, headworks will also come into the picture. And what is the principle? Gravity, we are going to use gravity. So, sedimentation is the principle. Yes, we were done with that, sedimentation. And then I am going to remove the suspended solids. Suspended solids, again typically sedimentation is my primary mode of removing suspended solids. So, some what do we say, organic content will also be removed. So, BOD or about 30 or 35% BOD will also be removed here. Yes, and then we moved on to looking at biological process, which we are calling as secondary treatment. Okay, this is secondary, this is primary. Primary treatment. Secondary treatment, what is the principle? I am using microbes, and microbes in the presence of oxygen will degrade the organic matter. Organic matter is the dissolved BOD or soluble COD, and they will go to the byproducts. Let us see, this is what we are trying to do. So, preliminary, primary and secondary are the biological process. Here principle we discussed this in detail, we will not go to that. And now we are talking about nitrogen and phosphorus removal, the nutrient removal. So, this is the tertiary treatment process, right, tertiary. So, this is where we are. In that context, we already looked at nitrogen. Again nitrogen, first we are going to look at nitrification, NH4 plus being oxidized to NO2 minus and NO3 minus by the microbes, and then denitrification. We looked at that, we will again relook at it today or in this session, but I will not look at it now. We will now discuss again slightly in slightly greater detail about phosphorus removal. What is the principle now? Unlike removal of the traditional organics or the BOD or removal of or degradation of nitrogen, we are not going to look at what do we say, phosphorus being oxidized or such. But how are we going to achieve removal of this phosphorus? We are going to achieve removal by phase separation. Phase meaning gaseous phase is one phase, solid phase is another phase, aqueous phase or the water is another phase, right. So, here I am going to see to it that the phosphorus which is in the aqueous phase is taken up by microbes and they are removed via sludge or into the solid phase and then settle down, right, that is the principle. But in general, these phosphorus accumulating organisms do not predominate, but I want them to thrive. So, I need to what do we say, see to it that the ecological pressure or the environmental conditions suitable to let these phosphorus accumulating organisms thrive, I need to see that those conditions exist. So, what is this condition? We looked at that. So, I will talk about it briefly and then we will look at it in more detail. For most people, the brief understanding is good enough. For those who obviously want to look at it in detail, you can pay attention to the aspects we will discuss after we look at this slide, let us say. So, one is anaerobic conditions, meaning we do not have any electron acceptors here, right, not anoxic, not aerobic. Aerobic, oxygen is the electron acceptor. In this case, we typically in the anoxic case, we will have what is it, NO3 minus as the electron acceptor. In anaerobic, we do not have oxygen or NO3 minus. And the next we will have aerobic conditions, let us see. So, when having this alternating conditions of aerobic and anaerobic, we are trying to put the system, when I say system, the microbes under pressure. So, sometimes during, not sometimes, during the aeration phase, they have the electron acceptor which is oxygen, right. They have carbon from the waste, yes, they have the carbon or the waste water is the source of electrons or the electron donor. Oxygen is the electron acceptor, so they can use this redox process to, what do we say, either for cell synthesis or for generating the energy needed for their growth, let us say. Yes. But when we put it in anaerobic, well, they are under stress, they can't thrive, let us say, the usual, what do we say, heterotrophs that we look at. But here we are trying to see to it that the conditions favor phosphorus accumulating organisms. So, let us understand why these can thrive while the others cannot. So, during the aerobic phase, what happens now? As we know, as I mentioned too, phosphorus will be taken in, right? Phosphorus from the water will be taken in and polyphosphates will be formed. During part of this, how does it work? A diphosphate plus PO4 3 minus will go to ATP, right? We discussed this earlier. This is part of it, right, which is involved in the, what do we say, phosphorus being taken up to form polyphosphorus, let us say, or phosphates being taken up from the water or wastewater, right. We see the phosphorus being accumulated to form polyphosphorus, right. And again, why is it that they are trying to do this? Because polyphosphorus is used as a source of energy. So, during this aerobic phase though, when electron acceptors are plentiful and such, they use this PHBs which they will accumulate during the anaerobic phase, right. They will use these PHBs, it is a source of carbon, it is a source of electron, right. So, and they will use the oxygen available here, readily available, right. And what is it now? This will go to either CO2 and H2O, or if it is NO3 minus is the electron acceptor here, it will go to N2 and such, let us see, right, depending on what it is. So, oxygen will be used to, what is it now? Oxidize the PHB, hydroxybutyrate, and then go to the end products. But where is this energy going into? This energy will be needed for this formation of polyphosphates, right. And also this energy that they gain when there is enough carbon, what do we say, sources of carbon and the electron donor, and also electron acceptor in the form of oxygen. So, they can thrive, right. So, they will use that also for cell synthesis and also for accumulation of this polyphosphorus. Why do they accumulate it here? Because in the anaerobic conditions, they will not have this oxygen or the electron acceptors. So, what do they do under this stress conditions? Under the stress conditions which we are trying to maintain by anaerobic, what do we say, conditions, these what is it now, fermentation products will be formed, and these phosphorus accumulating organisms like the fermentation byproducts. So, they will take these byproducts and they will form PHB, right. Why again? Because they can be used later. Why? We will come back to that. So, PHB will be formed, but for formation of this PHB from the soluble organics in the, or the fermentation byproducts here, from the fermentation byproducts, right, you will have the PHB being formed. For this they need energy, right, they need the energy. And how will they get this energy? By the transformation of polyphosphates, during which phosphorus will be released. So, from this energy will be released and that will be used to accumulate this PHBs, right. And in this process again you are going to what do we say, have the energy carried or the electron carried in this way. This is part of it, right. So, PO4 3 minus is being released, let us see, but we do not need to look at this in detail. This is a part of it which is involved in the formation of PHB, not PHBs, pardon me, polyphosphorus being degraded such that phosphates are released, right. So, again, what is the crux of this issue now? Here energy is being, what do we say, released internally from the polyphosphates being degraded to form PHBs. But why are they forming PHBs here? What is the role of these PHBs here? Why do these microbes do that? So, here everybody wants to thrive. Similarly, these phosphorus accumulating organisms want to thrive. They want to outcompete for the food whenever it is available later on, right, meaning in the aerobic phase. So, in the aerobic phase, right, as we see here, you already have these microbes, you have these microbes already having a source of carbon or an electron donor, which is the PHB. So, right, they already have a reserve of energy, you can think of it in that way. So, they will outgrow the other microbes that can thrive in the aerobic conditions. So, again, why is it that they are trying to do that? Because they want to dominate the microbial community, and these conditions we want to recreate, because as you see here, though phosphorus is being given out, here it is being taken up. And then we see that if we look at the net phosphorus uptake, it is relatively higher. So, all these microbes will take up the phosphorus and will remove them with the sludge. So, that is the aspect, keeping them under stress, right, alternating anaerobic and aerobic conditions. And then what will they do? These microbes will start thriving, and we just saw the reason. And we look at it in slightly more detail. This is from Bruce E. Rittman, Environmental Biotechnology, Principles and Applications, Bruce E. Rittman and McCarthy, let us see, right. So, here we have the anaerobic conditions where there are no electron acceptors. Yes, and as we discussed, what is happening out here, PHB has to be formed, and for PHB formation energy is required. Where is the energy coming from? Energy is coming from this what do we say, degradation, if I may use this layman's term, of polyphosphates into phosphorus. So, phosphorus is being orthophosphates or phosphorus maybe is being released, and energy is released, and this energy is used for the formation of PHBs, let us say, polyhydroxybutyrates. But again, as you see, within this you have some steps, acetyl CoA and so on and so forth, which is required for polymerization. And obviously, for the formation of this carbon, where is the carbon coming from? It is coming from the fermentation byproducts in this particular anaerobic condition. This is the anaerobic condition. So, here we see that they are accumulating carbon and electron donor source, let us say. And now, when it comes to aerobic conditions, later when the microbe comes into the aerobic conditions, what is happening now? Now, they have oxygen available, right, or nitrates available. These are the electron acceptors, and they already have the PHB available. With this PHB, polyhydroxybutyrate, which is an electron donor source of carbon, they can outcompete or outgrow the other microbes, let us see, right. They can use the carbon sources from outside, but more importantly, they also have stores of, if I say, energy or such, or carbon and electron donor here. And again, you can see it goes to acetyl CoA, and there is a cycle, right. And in this context, energy is released, and what does, or where does that energy go, or part of that energy? It goes into formation of these polyphosphates. Again, obviously, for polyphosphates formation, you need this phosphorus, and the phosphorus will be taken in from the solution, right. So, that is what happens. So, with this cycle, as you see in the aerobic cycle, you will have the phosphorus being taken in. Again, more detail here, you can look at that. Again, there is a role of acetyl CoA for which the energy is required, let us see, right, here at least. So, let us move on. So, again, MIT Open Courseware, we look at adaptation of the previous figure. So, what do we have here? This is the facultative bacteria that can thrive in both aerobic and anaerobic conditions, and during anaerobic conditions you have the fermentation products, let us see. Why is it that we want this? Because these fermentation products are liked by the phosphorus accumulating organisms, let us see. This soluble COD will go into formation of the PHBs, and the energy required will come from the polyphosphate releasing phosphorus and being degraded. And then in the aerobic conditions, obviously what is being happening? The reverse happens. Now you will have the PHB being degraded in the presence of oxygen, right. PHB is a source of carbon and source of electrons, let us see, and you have an electron acceptor, and these carbon and electron reserves will be used by the microbes for new cell production, and they will outgrow the other microbes. That is why they want to do this, and in that process, estimating that they will again be under stress later, they will take up this phosphorus to form the polyphosphates, which will be used during the anaerobic conditions again for a source of energy, let us say, for the formation of PHB. So, this is the cycle that we have, polyhydroxybutyrate, let us see, right. So, let us move on. So, phosphorus removal, as we mentioned, I guess I can skip this aspect. Let me see if I talked about the fermentation byproducts, okay, is released into the, okay, release occurs. So, in anaerobic conditions, let me just highlight this. Okay, under anaerobic conditions, phosphorus or orthophosphates will be released. Under the aerobic conditions, we will have phosphorus being taken up, uptake. So, that is something, but we can also look at the or view can also look at the details. And what else happens in the system, as in what happens to the soluble BOD. So, first, if there is an anaerobic case, obviously how is this going to be achieved? You are going to have recycle, but in one cycle let us see what happens. So, the wastewater is coming in here. Yes, influent orthophosphorus concentration is highlighted here, that is the influent orthophosphorus concentration. And let us see what else we have. We have the influent soluble BOD out here. So, this is anaerobic. In the anaerobic conditions, we know that facultative microbes will transform this particular, you will have the fermentation products being formed, and this fermentation products will be taken up by your bacteria, the phosphorus accumulating bacteria. That is why you see your BOD decreasing. And during that time, we know that the phosphorus will be released. So, that is what we see, orthophosphorus increased, let us say during this peak. Yes. After that, anoxic conditions, you will have nitrate as the electron acceptor. So, now you have what we say respiration in a way, and here O2 as the electron acceptor, and during this phase what is going to happen? Obviously, phosphorus is going to be taken up. Bacteria will store phosphorus during growth to compete for BOD when they get back to the anaerobic zone. Well, that was explained in a slightly different way, but net is that you will see phosphorus. Though you see initial increase in phosphorus, if you look at the net phosphorus here, it is much lower than or lower than the initial concentration of phosphorus, and obviously you see that the BOD is decreasing, right. And then second anoxic reaeration and such, obviously later you will have recirculation out here. So, stress, no stress, stress, no stress, and the bacteria that can best adapt to it will be the ones that will thrive. So, I guess in a different way, that is what is mentioned in a clearer picture out here. So, anaerobic conditions, phosphorus is being taken up, soluble BOD will also decrease, and orthophosphorus will be, pardon me, it will be released here in the anaerobic conditions. Aerobic conditions, phosphorus will be taken up into the microbes, that is why the orthophosphorus in the water or wastewater will decrease. All the time soluble BOD will decrease, right. And then obviously you are going to have recycle of the water, so that the microbes, you know, over time understand that they are going to be put into stress, that is why they take up the phosphorus here, right. So, let me just summarize nitrogen removal. Why? Because we are going to look at aspects we looked at earlier, as in the kinds of what do we say configurations where you can achieve nitrogen removal. We did look at it briefly earlier. I also want to spend some time now, because you can then compare it with what do we say phosphorus removal configurations. Nitrogen removal, what are we trying to do, or how do we try to achieve that? Primarily we have NH4 plus, and then in the presence of oxygen we will oxidize it to NO2 minus and then to NO3 minus, ammonia oxidizing bacteria and nitrite oxidizing bacteria. But NO3 minus is very soluble, I still need to remove it. So, how do I do that? I will see to it that this is used as an electron acceptor, but for this to be used an electron acceptor, oxygen should not be there, right. If not, oxygen will be the preferred electron acceptor, because more energy is released that way. And obviously, what is the electron donor? Organic compound is the electron donor. And then at the end of the day, you will have formation of nitrogen, which is gas, and then can be released into the atmosphere, let us see. And thus you are going to have denitrification here and nitrification here. Nitrates are being formed, that is thus nitrification. What do we say? Nitrogen is being removed from the system by formation of gas, which will leave the water. So, denitrification. So, let us look at the configurations once. Let me change my ink color. So, nitrification and nitrogen removal. So, here let us say nitrogen removal, and we have the conventional activated sludge, right. This is the conventional activated sludge. And what do we have here? BOD, and depending upon the solid retention time, the sludge age and the oxygen concentration, you will or can have nitrification. So, during that nitrification, obviously, or during this BOD aeration, you will have the soluble COD being decreased, let us say, and ammonia too will be degraded depending on how you are maintaining it. If ammonia is being oxidized, pardon me, nitrates will also increase. But when will this typically take place? Only when most of the BOD has decreased, only then will ammonia start being used as an electron donor. If not, the preferred electron donor is the organic matter. Only when most of the organic matter has been degraded, well, ammonia, what do we say, degradation come into the picture. That is one thing, and that is why you see an increase in the nitrate formation out here. So, this is what we have, right, but then you will have a lot of nitrate in the outlet. So, ammonia comes in, nitrate is going out. Nitrogen removal is due to cell synthesis, let us say. As we know, 12% of nitrogen will be taken up by the microbes, right. So, that will be the nitrogen removal, and then I still have nitrogen here. So, what can I do? There is a process, I guess, Workman process. So, again we have the same system as earlier, but now I am going to put up an anoxic tank after the aeration system, anoxic. So, what is going to happen during the anoxic phase? Endogenous meaning the bacteria will use their own cells for or will feed on their own cells or cell matter. That is endogenous what do we say, respiration, if I may say so. Why? Because as you see here, by the time it comes into the anoxic tank, you do not have the what do we say, carbon source anymore. So, they need a carbon source for cell synthesis. We looked at the reactions earlier. So, you know, they are going to feed on their own cells, right, and here we have nitrate, as you know from earlier case, and nitrate will decrease again in this particular system, let us see. Endogenous respiration is the carbon source, and typically that is slow. So, this denitrification rate is slow, but to improve this, what can I do? So, effluent quality looks like total nitrogen will be 15 milligram per liter, which is not too low. So, to sustain this, this is the ratio of COD to TKN, right, organic and ammonical nitrogen to sustain it, but with in general this is not possible without supplemental carbon source. So, I need to add a carbon source or an electron donor source. So, I typically add methanol, let us say. So, with that methanol, what is the profile going to look like? So, this is what we see, the red dotted line is increasing because I added methanol, the COD is increasing, and then is decreasing because, why is it decreasing? Because the microbes are using that as an electron donor, methanol is being used as an electron donor, and nitrate which was there is being used as the electron acceptor, and then you have the relevant denitrification N2, and that is what you see out here, right. So, this is one particular way to go about it. Let us look at another configuration here. So, here we have the anoxic tank before the aeration tank, right, and let us see how the profile is going to look like. Theoretically, you will have denitrification, but when will you have, or what will be denitrified here? Whatever nitrate is coming into the picture, or the nitrate that is in this aeration tank which is being recycled will be degraded to N2. But obviously, the issue is that you will also have nitrates leaving the system, which is not something that you want. So, let us see what else or how this system is going to look like. So, COD by TKN, COD by TKN greater than 12. So, you do not need to add an external carbon source. Why? This is fresh waste water. So, typically even though with recycle the COD to TKN ratio is available. So, soluble COD and nitrate though is relatively less, you know, even though you recycle that, right. Okay, so that is the decrease in COD and the decrease in nitrate, which is not great though, right. Wastewater is the carbon source, you know, it can go faster, but it is not because there is not enough nitrate out here. So, what can you do? So, this ratio Q is to QRAS, return activated sludge, the Q is to QRAS is important. A higher QRAS will influence the denitrification efficiency, right. Pre-substrate denitrification reduces BOD load on aerobic zone. Why is that? Here I need to put in money to pump in oxygen, right. But what is happening, what am I trying to remove? I am trying to remove organic matter here. Organic matter will have to be degraded in the presence of microbes by oxygen, right, or in the presence of oxygen by the microbes, but some of the organic matter will be degraded here itself, NO3 minus, for which I am not supplying any oxygen. So, right, that is why it will decrease the BOD load on the aerobic zone. So, effluent quality relatively better than earlier, but again still not pretty good though, right. So, that is one aspect. So, modified Ettinger process. So, what do we have? This is the similar system as what we had earlier. Let us see, but then we have an internal recycle, right, and looks like this internal recycle is 2q to 4q. This is q, this is q RAS, and this is 2q to 4q. Why are we doing this? For example, earlier we saw that here we do not have a lot of nitrate here, right, and if I can get that or more nitrate here, then obviously I can improve the kinetics in this part of the system, but I cannot increase the return activated sludge to whatever level I want though, right. It is going to depend upon the mass balance. The RAS, return activated sludge, is going to depend upon the mass balance, and only then will I know how much I can pump again or such. But without what do we say, disturbing that, what can I do? I can look at the internal recycle of the MLSS or such, 2q to 4q. So, nitrate is being recycled, right, though some nitrate, but now only relatively less nitrate will leave the system. We will see why total in general. So, soluble COD, higher degradation during this anoxic phase. Why is that? There is more nitrate. So, efficient carbon utilization and higher nitrogen removal, and during aeration you have further removal of the COD or BOD, and during aeration you have nitrate being increased, but again because it is being recycled, let us say they are in effect saying that this is what it will look like, let us say. So, in general net you will have a greater nitrate removal. So, the source of nitrate for the anoxic tank is not only from the return activated sludge, but from the internal recycle. So, let us see what else we have here. Internal recycle rate obviously important, higher increases the denitrification efficiency, and obviously as you can see total nitrogen here is pretty low, and this is the 4-stage Bardenford process. Let us see what we have. We have denitrification, nitrification, anoxic tank here, aeration, and internal recycle here. This is more or less the same as what we had earlier, right, internal recycle and the general sludge, let us see. But what else? Again we have a denitrification second anoxic tank. So, what is going to happen? Similar profile until now, and here you have further denitrification, right. So, this level of nitrate 2 is being removed because you have a second denitrification tank, let us say, so nitrate polishing tank. Earlier case you had only the one anoxic tank before aeration pre-substrate. Now you have an endogenous one. So, in this endogenous, am I supplying anything? No, I am not going to supply any oxygen, right. I am not going to supply anything. I am not going to supply any methanol. Why? Because I want the residual carbon or organic compound also to decrease, let us see. So, I am not going to add any methanol. So, the remaining, what is it now? Nitrate and remaining organic carbon, or the what is this, organic carbon or endogenous respiration by cell mass being used for respiration will take place. That can affect the quality of your this thing, but you have to maintain it at the endogenous growth phase. So, this is the 4-stage Bardenford process, right. Okay, then aeration to strip your nitrogen. So, aeration here improves settling by stripping nitrogen. So, nitrate what is it, nitrogen gas will have to be removed. So, you will bubble air through it, and that will strip the air, what is it, nitrogen from your system. So, here much lesser total nitrogen 2 to 4. This is now being, I guess, used especially in cases where nitrogen is an issue, right. So, let us move on. Phosphorus removal, we already discussed the aspect. But here we are not requiring or not looking at just anoxic process, we want anaerobic process, no electron accepted in the form of nitrate or oxygen. So, let us see what the configurations look like. So, we have the evolution of the biological phosphorus removal, initially A by O process. So, this is the typical activated sludge process here, right, and you can have anaerobic before. So, what do we have net here? Anaerobic or stress conditions, and then no stress conditions, and then recycle. So, these microbes which are being continuously recycled, what is it that they are experiencing? Stress and no stress. So, here they are going to accumulate that PHB while releasing phosphorus, and during this phase they will use up that PHB, right, use up that PHB that they stored so that they can outgrow the other microbes. And where is this energy going from? This not going from, where is the energy from this degradation of PHB going into? It is going into formation of the polyphosphates. For formation of polyphosphates, what is needed? The phosphorus from the water will be taken up, let us see, right. So, that is how phosphorus removal will take place within this aeration system. So, what are the issues here? Phosphorus uptake, phosphorus release, let us see. So, COD is decreasing, fine. Why is this increasing slightly? Because as you know, in the anaerobic phase, phosphorus will be released when the polyphosphates are being degraded to give energy for formation of PHBs, right. And some of it is decreasing, not a lot of the soluble COD. Why is this? Fermentation products, and then they being taken up by the microbes and such, or even for cell synthesis of some microbes. In the aeration tank, obviously kinetics is faster. Again, phosphorus will be taken up, that is why it is decreasing, but as you see, R net is not great. Why is the R net removal, let us say, or net removal of phosphorus not very good? Well, because when you are recycling it here, you see that there will be some oxygen here and also nitrate certainly, right, and that nitrate is coming into the picture here. And as we looked at the thermodynamics, if you have nitrate or the relevant what do we say, electron acceptor, like some oxygen or at least nitrate, which is an electron acceptor, they do not let your phosphorus accumulating organisms thrive. Denitrifiers or such might thrive, let us see, right. Let us see what else we have. So, this is the COD and phosphorus removal there, right. Phosphorus increase and then decrease, inefficient carbon utilization, inefficient phosphorus uptake, let us see. COD to total phosphorus must be greater than 40:1, system must be phosphorus limited. Effluent total phosphorus is around 1, let us see. Why is it? The nitrates and the oxygen inhibit P release in the anaerobic zone. It is not really an anaerobic zone, so difficult to maintain anaerobic conditions. So, this A2O process is widely used, at least in India. Let us see what it is about. Here also you have the aeration basin, before that you have the AX is, I guess, for anoxic. So, this will in a way remove nitrogen, that is something we looked at. So, that is why I wanted to look at nitrogen removal also earlier. So, we are now looking at nitrogen and phosphorus removal, right. So, earlier it was primarily looking at phosphorus removal, here in a way we are looking at what is this, nitrogen and phosphorus removal. So, it is A2O process. So, what do we have? Anoxic tank here, aeration system out here with internal recycle. Internal recycle, nitrates form here, will come here. In the anoxic tank, you are having denitrification, fine. So, with the addition of this anaerobic zone, what are you going to have? You are going to try to achieve phosphorus. Now, let us look at the system. So, we have the soluble COD decreasing and such, let us see, right. Okay. And why is it relatively better? Because as we looked at it in the case of nitrogen removal, with the internal recycle, the nitrate concentration that goes through to the clarifier and is returned to the anoxic tank will be relatively lesser. That is what you see, recycle of NO3, let us see, right. So, that is going to be pretty less. So, the anaerobic conditions are pretty well maintained, no source of electron acceptor like NO3 minus or such, let us see, right. And what else is happening out here? Phosphorus, as you can see, is being taken up both during the aerobic phase and during the nitrification phase. So, efficient phosphorus uptake. So, phosphorus released during the anaerobic system, not much during the denitrification what do we say phase, when obviously nitrates are present in a lot, let us say, and then slowly you have the phosphorus uptake happening in the aeration. And then during nitrification phase, I guess you have a lot more efficient phosphorus uptake, let us see. And what is happening to nitrates? This is increasing right here. Why is this? Because there is a recycle coming in. So, nitrates are increasing and then denitrification is taking place. So, nitrates are transforming into N2 during denitrification, and then they are increasing because NH4 plus is going to be oxidized to NO3 minus. So, they are increasing and then recycle is occurring here. So, that is how we are more or less getting nitrogen and phosphorus here. So, total nitrogen is 8 and total phosphorus is 1. So, we are getting more or less 8 and both nitrogen and phosphorus removal, let us see. But again, depending on the level it is, how efficiently you maintain, If NO3 is present here, it will inhibit the phosphorus release, let us say. So, looks like we have another variation. We will just look at 2 more variations and end the session. So, what do we have here? So, this is what we looked at until now, right, but the issue was that here the nitrates, if any, or those which might be present in this waste or return activated sludge will affect the phosphorus, what do we say, accumulating organisms here, or phosphorus release here. Without phosphorus release, they can't store the PHBs, let us see. So, let us see what are they doing. They are saying that okay, I won't recycle it before the anoxic tank, but I will recycle it just before the, not before the anaerobic tank, pardon me, but just before the anoxic tank. So, this way the nitrates, they are not coming into the picture, they are not, what do we say, coming in contact with your anaerobic phase, but they are directly going into your anoxic tank, right, nitrates, right. And then obviously you need to have a internal, what do we say, circulation. Why is that? If not, if it is just straight flow, there are not going to be any microbes in the anaerobic tank, let us see. Obviously you need to have recirculation here. So, here you are going to have anaerobic conditions, not anaerobic, anoxic conditions, but nitrate is being degraded to N2, right, and you have system that has relatively less nitrates at the end of the system. So, if I recycle from here to here, the nitrate concentration will be relatively less, and anyway influent wastewater, I know that oxygen concentration will be relatively less. So, anaerobic conditions are relatively better maintained. Let us see the second internal recycle, which is this, enhances the phosphorus release by returning residual carbon to the anaerobic zone. Return activated sludge enters the anoxic zone to isolate anaerobic zone from the residual nitrates and DO. That is something we already discussed. So, I guess relatively better total nitrogen removal, let us say. And then the evolution of the BPR process. Earlier for nitrogen removal, we looked at 4-stage Bardenfo process. For nitrogen and phosphorus removal, we see something called 5-stage Bardenfo process. So, let us look at what this is about, let us see, right. Earlier I think this was our 4-stage Bardenfo process. We had a denitrification tank before aeration system or aeration tank and internal recycle, and then we again had another denitrification tank where it was endogenous respiration, as in the cell mass itself is being used as the source of carbon or the electron donor, and NO3 minus was the electron acceptor. And then you had the aeration to, what do we say, remove this, remove your nitrogen from the system, right. The nitrogen that is given out during the denitrification, you are, what do we say, supplying air to strip the nitrogen from the relevant system here. And so, here what do we see in the aeration system, phosphorus uptake will take place because we are again pumping air, some more phosphorus uptake will take place in this aeration. And by adding this anaerobic tank here, obviously for the system to experience stress and see to it that phosphorus accumulating organisms thrive well, what do you need? You need alternating conditions of anaerobic and aerobic. So, obviously we have aerobic, but now obviously we need the anaerobic tank also. That is why it is called the 5-stage Bardenfo process. But here I guess rather than putting it up here, they are going to take the recycle much further there, right. So, add second aerobic reactor to strip nitrogen and polish phosphorus uptake. Again with more aeration, more phosphorus will be taken up, reduces in what do we say, internal recycle requirements. So, now you see phosphorus pretty good, total nitrogen also pretty good. Again the whole thing is to understand that you need carbon source or electron donor, and you need an electron acceptor, that is for aeration and denitrification, let us see. But for phosphorus you need anaerobic and aerobic conditions, and that is how you try to play around so that you get the relevant what do we say, optimum conditions, right. So, metal salts sometimes you add them for chemical precipitation of phosphorus, and you can add methanol if you want to increase the denitrification, but again that depends on what is the residual carbon content here, let us see. So, additional, what do we say, variations of the BNR process, but maybe these we will ask in the relevant quiz or such, but we will just have this information here so that this can be asked in the relevant quiz or the homework, let us say. Modified UCT, Johannesburg and so. Anaerobic, anoxic, aerobic, so different what do we say, variations, but we will not go into detail at this stage here. So, phosphorus, as we mentioned, can also be removed by chemical precipitation. Precipitation meaning if I have a relevant compound that is dissolved with the relevant ligand or such, I can see to it that the compound which is dissolved after reaching a certain threshold will precipitate out, as in I am changing the phase. It is now not in the dissolved phase or aqueous phase anymore, it is now in the solid phase by dissolving out, right, not dissolving out, by precipitating out. So, that is what we see. We have the relevant salts that you can add, and you have the phosphate here, right, it is PO4 3 minus, and then again if there are any stoichiometric issues you can figure that out. So, Al 3 plus, right. So, that is why you have this aluminum what do we say, phosphorus, I guess, aluminum solid being formed with aluminum and phosphate, and that is how you can remove the phosphorus. But in general, if you can get the biological process right, that is better, because here you are adding, what do we say, TDS to your particular system. You do not want to add total dissolved solids to your system if you are looking at sustainability, let us say, right. So, again phosphorus removal, rapid mix with along with alum, secondary effluent, and then you can remove it, and the usual reaction basin and the settling basin, let us say. But again depending on how well you are operating it, or if you have an old plant for which you do not have the space to what do we say, look at removal of phosphorus by the biological process, then you can go for your chemical process, let us say. So, with that I am going to end today's session. Thank you.